All right, welcome back. So this next section, this video, is a overview or a summary of machine learning techniques that we've talked about so far, and it has a number of illustrations in it. All right, so let's get started. Now, this particular topic, if you're watching it in order with the other videos that go along with this, then what you'll see is that we're kind of at a special point in what's being presented, or what's in the whole course. And what we've seen so far up till now is that you've had a number of lectures, and the lectures have been both in the topic of mathematical theory topics and also in computer science tools. On the theory topics, we've seen topics like regression and correlation and classification and things along those lines. On the tools topics, you've seen the sample notebooks that have Python, of course, but NumPy, Pandas, and scikit-learn, and so forth. So you've seen a number of tools and the theories that go along with them. And then in parallel or separately, we showed you the example of the Titanic notebook example. Titanic notebook is a really good example. Of course, what happens in that notebook is that we've taken a look at all of the data. We've input all of the data on the passenger list of the Titanic. There's a number of features about that passenger list. For example, the age or characteristics of each person, or what kind of ticket they bought, and so forth. And based on that data, we've cleaned it, we've put it into a very particular format, and then from that format, a number of machine learning algorithms were used to make a prediction on whether a person with those characteristics would have survived or not survived the disaster of what is, of course, the Titanic. And what we're going to do today, actually, we're going to go, I'm going to say, a level deeper into the algorithms that you saw. It's one thing to be able to call those algorithms in the code and, for example, in the notebook. It's another thing to understand what the algorithm is actually doing. And what I mean by this is a special point in the course. While all of that theory and lecture has been going on, we've basically gotten to roughly this point on the course where, from a project point of view, you've developed a story, and you've also had what is the low-tech demonstration. So you've come up with what is the story of the project that you're about to build. At the same time, we have a number of both tools and theoretical models that we've been introducing up till this point. And so from here, this is almost a minimal set of information that you can use to really do a lot of different types of projects. All of this has been integrated together, if you want to think of it that way. Okay, so from here, this should give you a pretty good jump start into getting going with the project. All right, now, let's start with the overview or review of machine learning topics. And so far, really what we've talked about is supervised machine learning. We haven't really talked about anything that's not in that category. And from an illustration point of view, I mean, if you just want to think of it in pictures, basically that means that you've got sets of data, or you've got elements of data. Usually each of these pieces of data refers to a row in a table. But in the terms of a picture, we'll just think of it as sets of data. And some of that data in this example, some is labeled with a dark circle, and some of it is labeled with an open or a light circle. And this is the data that you have to basically train with, and that there's other data that you haven't seen so far. So you learn from the data that you're going to use in the training, and you will use it to attach labels to some of the data rows that you've never seen before, right? And that's basically what supervised machine learning is. Now, when we see it from a code point of view, or when we see it in real life, we don't see it as pictures. The way we see it is as tables. So we'll have data, and usually you have a table of data, and we often refer to that as X, and that is many, many rows, and each row is one of the elements of the data, and then each column is a different feature. So you might have one, two, you might have many features in that table of data. And then you've got Y, which is basically your labels. So in Y, you would say whether, in this case, is it a filled circle or an open circle, or whatever way that you want to categorize each of the rows. Now, we'll be given a block of data that we can learn from, and then there's a set of data that we don't actually see in this first code. And the data that we get in order to learn from, we use that in order to build a model, and then later a much larger set of data, which is of course not in this code that we're showing right now, will be used to make your predictions or to make your classifications. Now, since we've got this block of data, which is in sample, not the out of sample data that we don't have yet, but out of this in sample data, typically what we do is we'll break that into two components. There's a part which we use for the training, and then there's another part which we will use to test our model. If we use a part for training and then we use the same component for testing, then of course we might get better results than if we trained on one part of the data and then we tested on a part that we had never seen before. Now, when you look at it in code, and that's this like super basic, simple example on the right here on this piece of code here, X appears just as a matrix, and what we'll do is we'll just use in Python the idea of slices. So what we've done is we've taken the first 500 rows of X, and in fact we did the same thing, the first 500 rows of Y, and we're going to use that as our training data. So we gave it a name, X train, and Y train is the part of the full table X that we're going to use for training, the first 500 rows, and that we'll use another part of it, X test and Y test, the second 500 rows that we'll use to test the algorithm or model that we learned from in the first 500 rows. Okay, so that's the very basic idea so that we can get started. So the first of the code samples that we showed you, the first idea that we showed you with the machine learning algorithms was linear regression. And the basic idea, of course, is that we took all of the different values, which are like the different dots from the table entries, and we use the math, just like we talked about before, to draw a line that best fits through all of the points in the table. And of course, that line could be a hyperplane, depending on how many different features or how many dimensions that we were talking about. So when we look at this now from a code sample point of view, and we did this using our scikit-learn library that we could import from, it turns out that it's pretty straightforward or simple. There's really not much to this code. In fact, the fact that you can do it in only 3 or 4 lines of code is really what makes this so powerful. So if we look at it, first thing that we're doing, we are importing the model scikit-learn linear model, so that lets us have access to the linear regression code. And then we're going to instantiate a model. So in this line of code, what happens, model, we're creating it, is equal to, and then here, linear model dot linear regression. So basically, we've created a model for linear regression. And all we have to do now is take the table, which we're using for training, meaning X, and the labels Y, which we're using for training, and use the method fit. So model.fit, we're going to fit in the data, which is X-train and Y-train. And so after having done that, what we've basically done is decided what is this best line that fits through all of the data. And that basically means what is the angle or the slope of that line or hyperplane, and that's usually set in the parameters. If you think back to the theory lecture, that would be the parameters that make up the W matrix, and of course the offset of the hyperplane also. So all of that gets learned when you put in X-train and Y-train into the fit method, and then that will go away for, you know, half a second or something for some short period of time. And now you're able to do predictions. So now you can use a separate method, model.predict, and you put in X-train, for example, the same data that you used earlier to parameterize it, to set the parameters. And if you did that, what you're going to get is a guess of the Y values which go with it. So for any given X value, you'll get the predicted value Y. And that's for the data that we used to train it with. You can also then test it. In other words, you can see not only how it does on the data that you trained it with, but you can test it using data that it's never seen before. And so that would be putting in the part of the X matrix, which we called test, which, if you recall the last diagram X, there was a part which was for training, and there's a part for testing. So now we're going to use the second part of it, which had never seen before, use model.predict with that as an input, and we will get a set of values which are predicted based on the test value. And of course, we've got the ability, we didn't do this in the code, but we could find out for every actual value of Y and X, say this dot right here, we could find out for that particular value of X, the actual value of Y versus the predicted value of Y. We can see if they're the same or if there's a difference. And if there's a difference, then you can think of that as an error. And we can take the average of all of the errors, or we can take the average of all the square of the errors, and we can get an understanding of just how accurate or how close to the actual values is the model which we made for this data. Okay. Okay, so what we just looked at so far is an example, a code example using scikit-learn, and we used linear regression. And we used our table X. We used our table X and the labels Y, and basically we're able to use about half of that data to train. And then we used the other half of the data to be able to test how good our model is based on that data. Now, it brings up a natural question. What if you don't have very much data to do the training and the testing with? That is, you only have so much data, and then you're going to be using it later on data that you've never seen. So one option is that maybe you use a small amount for the training. Like, so let's say, what if you only used a small amount of all the data that you had to train with? Well, the issue with using a small amount of data is that your model may not be very accurate. That is, that you can use a small amount of data to train, but then when you try to test it on the data that you've never seen, you're not likely to get very good predictions. In other words, the variance could be high. So high variance and basically low accuracy. Another possibility is that you use almost all of the data for training, all of it, or almost all of it, to train. And if you do that, then maybe you can get actually much more accuracy on the model. Maybe you can fit the data very well, and that you might test it only with a small fraction of data that you have remaining. But in this model, what may happen is that you might actually overfit the model, meaning it works great for the data that you trained it with, which is most of what you have, but it doesn't necessarily work as well on the data which you will test it with, and it may not work also as well on the data that you have not yet seen. So the issue with that is basically, yes, you used a lot of data in the training, but now you might have overfit, or you could think of it as a type of bias that's biased towards the data that you use for training with. So now the question becomes, well, you only have so much data that you can use for both training and testing. What can you use to make this data, to basically use this data most efficiently? So the most common solution to this problem, the problem being having only so much data that you can use for the training and testing, is to use something called cross-validation. And we've talked about it a little bit, but we can just summarize it here. Cross-validation is basically taking your data and dividing it into pieces that you use these combinations to both train and test. For example, you can have the data divided into 3 pieces. And if you did that, you would call that threefold. You know, you'd say KFold cross-validation. You can divide that into 3 folds. In other words, having these 3 components. You can also have K equals 4 or 5, so forth. It could be 5-fold or 10-fold cross-validation. It's very common to pick a number, K, between 5 to 10. Typically, you'll get something like this, where you divide it into 5 or 10 different subsets of all of your data, and use this as part of the model for training and testing your data. Now, if we stick with the example that K is equal to 3, then what we would do is we'd say, okay, then we'll take section 1 and 2, in other words, here's fold number 1 and fold number 2, and we'll train it with these 2, with 1 and 2. We'll train and train, and then we'll test the result that we get from those 2 with this last piece, which would be the 3rd one. And then we could do the same thing. We could take blocks or folds 2 and 3, and the result of that we could test against block 1. And then, of course, the last combination, we could try the first one and the 3rd one and use those 2 to test with the 2nd one. So that would be 1 and 3 and tested with number 2. And in each one of these, you would get an error. Maybe you get an error value 1, an error value 2, and an error value 3, you can take the average of these three and get a total error value, or an average of how accurate the model is. So this would give you a better estimate of whether this model is likely to perform well or not so well on the data that you haven't yet seen. Now, if you want to actually do KFold cross-validation, also should point out that you don't have to necessarily write all of this code yourself to do these things. Built into scikit-learn is a library function that will do this for you, and you can look that up. All right. We should mention the basic procedure of KFold cross-validation. So the steps are typically that first you take your whole data set and you shuffle it so that you have all the rows randomly shuffled. Then you split it into the K groups. Like I said, that's usually a number from 5 to 10. And then for each unique group, you take one group and hold it out from the rest. You take the remaining groups and use them as a training set. Then, of course, you'll fit the model using the K-1 that you are using for training, and then you can evaluate it on the one that you are holding out. And then you remember or retain the evaluation score, and then you do this again. So you go back and you do it for every possible fold, every possible of the K different folds that you can hold out. And then, like we said in the earlier slide, you can take the average, or basically be able to summarize the model from all of the different K experiments that you just did. Okay, and once again, you don't actually have to write this code because KFold cross-validation can be done just using the library calls that are part of scikit-learn already. If we want to review what we've looked at so far in this section, first, we set up this section with a discussion of the context of the Titanic notebook. In that notebook, we take data, which is basically a passenger list. The data is cleaned, put into a certain format, and if you recall from the other section, it's used to predict through classification whether or not a passenger would have likely survived or not survived the Titanic disaster. So in this section, what we did was we reviewed how the data is basically formatted and held in tables, and in particular, how a portion of that data is structured for training and how it's held or structured for testing machine learning models. Then we took one example, not very many lines of code, relatively straightforward, but an example in Python and using the scikit-learn library. And that's an example for linear regression, which is a type of prediction, although not the type of prediction that we used in the Titanic notebook. And then building on the topic of regression and on that particular example, we looked at how do you use the data that you have for both training and testing in the most effective or efficient way. And for that, we talked about cross-validation, in particular KFold cross-validation. In the next section, we're going to take a look at machine learning algorithms that are used for classification as opposed to regression. And those will be the same ones that were used in the Titanic notebook example as well. So that's what's coming up in the next section.